Hi, folks. Today's topic is transformations of parent functions. We'll talk about what a parent function is in a minute, but this is one of those topics that, it's like factoring or like solving. I mean, these are things, this is a topic that you're going to see over and over and over again. This is one of those foundational ideas. So the idea is that you could take any function. This is what we call a parent function. It's like it could be a quadratic, could be a cubic, it could be a root function. There's all sorts of different functions. And these affecting the function by multiplying out front or doing this, subtracting something next to x and adding something at the end, no matter what the picture looks like. It doesn't even have to be like a normal function. It could be any function, any graph that you could come up with. These characteristics applied to the function, we call them transformations, will create the same results. So let's go through and talk about what each one of these pieces will do. But my point to you is that these will affect every single graph exactly the same way. It'll do the same thing to every single graph. So let's start off by highlighting these two. Any graph or any function, if you add or subtract something next to x or add or subtract something on the end of the function, it's going to take that picture and it's going to shift it. These are called shifts. Anything added or subtracted onto a graph is going to shift it. So as long as it's in this format, I mean, I guess we could get kind of technical on general form versus vertex form, but these are shifts. The thing next to x obviously would shift x, but a little bit weird, and that's why we use a subtract symbol here. It does the opposite of what it says. And I'll talk about that when we get into an example, but like this one, this is going to shift this graph to the left 3. It's going to move it left, not forward 3 like it kind of looks like. It does the opposite. And then this is not connected to x, so anything not directly connected to x always affects the vertical or the y. And this, because it's a plus, this ends up being the same. So in other words, this -4 is going to shift this picture down 4 spots. So those are the shifts, and then the other two things, you're going to either get a graph that gets stretched, shrunk, or neither, and then our graph is going to also get reflected. And they both come from this multiplier out front. So this multiplier out front, I'm going to draw the arrow after I write this stuff because it's a little bit easier, it looks a little bit nicer. These control reflections. So remember, a reflection is, let's say you have a parabola. Parabolas are these graphs that go like this. If I put a negative out in front, that reflects it, and now my parabola looks like that. It points downward. So it's a reflection over the y-axis. So our graph reflects, yes. Our graph will reflect if that a value is less than 0. Or in other words, we could also say that it's negative. There will be no reflection if a is greater than 0. In other words, if a is positive. So this a value determines reflections. This a value also, that's not a very good arrowhead, this a value also determines whether our graph is going to be a stretch, a shrink, or a neither. Well, let's think about what kind of numbers, I can probably circle this and draw my arrow. What kind of numbers would make other numbers get bigger when you multiply? Well, actually, let's go to neither first. This one probably makes the most sense. What number could you multiply by that would not make the number bigger or smaller and leave it the same? Well, hopefully you said 1. Now, we got to be a little bit careful here. When I'm talking about stretch, shrinks, or neither, I'm not also talking about reflections. Those two, that number has to be, all I care about is the value of the number. I don't care if it's positive or negative. We call it the magnitude. So I'm going to look at the absolute value of a. So let's say that that's a -1 out in front. That means that I have a reflection. The negative means a reflection, and the 1 means that our graph is a neither. It didn't get stretched or shrunk. Well, if a equals 1 is neither, we would have a stretch if A is bigger than 1. And we would have a shrink if absolute A is less than 1. I always forget to say absolute, but I wrote it down. So when I'm talking about a stretch, a shrink, or a neither, I can have a negative number and still be considered a stretch. So if there's a -4 out in front of this, this is a stretch in the negative direction. Okay, so these are called the transformations. Now we got to talk about what a parent function is. So I want to now switch sheets and go to our cheat sheet that we'll be able to use our parent function sheet. This is one that, this is one of the few documents. There's lots of good stuff that we do in this class, but this would be a document that I would definitely hold on to, because you could potentially, depending on your college teacher, see yourself using this again. So this is something that you can use on the test. So you can use this on the test. You cannot add anything. Unless given permission. So as we go through this unit, if there's something that you think, for instance, that we're going to do in the next unit, we're going to do graphs of rational functions. And there's a whole list of stuff that helps us graph that. We're going to put that, you're going to be able to add that to this. But don't add anything without my permission, because then I'll have to deal with it on test day, and it's not a fun thing to deal with. All right, so let's talk about the parent functions. Now, I made little charts down here. If you want to plug in chug, if you want to take, like, here's my equation, and you want to plug in 0 and plug in 1 and plug in 2, that's where I'm getting these points. I would rather just think about how these functions behave and how they move. So a quadratic function. So let's take a quadratic and start off. Let's start off at 0. What's 0 squared? 0. And then as a quadratic, as you move over 1, I always like to think about this as moving from the origin. So 0, 0, 0 squared is 0. Then from there, if I move over 1, what's 1 squared? 1 squared is 1. Then I'm going to go back to the origin. It's not like slope. You know how slope, you just keep building off of that, the point that you got before. This is different. You go back to the origin. Instead of going over 1, up 1, now I go over 2. Well, what's 2 squared? 1, 2, 3, 2 squared is 4. Now look, this says you must graph 5 unique points. So we've got 3 of these points already figured out. Let's go the other way now. When I go -1, that's like taking -1 and squaring it. -1 squared is 1. And then -2 squared is 4. And that's why we get this sort of curvy shape called a parabola. So you really want to think about how parabolas move. And if it helps, you can keep plugging and chugging and make a table. I know Musio loves to make tables. And so if you like the way she did it, go for it. Just make little tables and you can work from there. But I'm going to teach it. I'm always going to talk about it in terms of how the function moves. Okay, so let's start with our cubic function. 0 is so easy to plug in. I always just plug in 0. So 0 is 0. Now I think about how the function moves. That means I go over 1. Is 1 a nice number to cube? Yeah, 1 cubed is 1. So then there's my next point. Now I go back to the origin, and then I move over 2. I take 2 and I plug it in. 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. Now I'm going to do the same thing for the negative side. -1 cubed. Now this gets a little bit interesting. A negative times a negative is a positive. So when I squared -1, I had a positive. But a negative times a negative times another negative, -1 cubed, is still negative. 1, 2, 1, 2, 3, 4. And I would get -8 when I plug in -2. So this is the parent function for cubics. The cubic parent function. Let's move on to absolute value. Yeah, this might be a worthwhile time to jump in here and talk about oddness and evenness. Oddness and evenness. An even function is a function that reflects over the y-axis. We're going to get a lot more into that when we do the notes on it, but I just kind of want to give an introductory idea there. An even function is a function, well, that's a weird looking E. An even function is a function that has reflective symmetry across the y-axis. An odd function has rotational symmetry around the origin. So in other words, if I grab this side of the graph and I rotated it, use this as the spinning point, and I rotated 180 degrees, if the graph looks exactly the same, that's what we call an odd function. Okay, so let's talk about absolute value. I'm going to start off at 0, 0 again. So what is, let me get a good color here. What's the absolute value of 0? Well, let's do a quick little note. Let's do a reminder here. What's the absolute value of 7? 7. What's the absolute value of negative 7? 7. So the absolute value will always make things positive. If it's already positive, it stays the same. It doesn't switch the signs. It just leaves everything positive. So absolute value of 7 is 7. Absolute value of negative 7 is 7. Absolute value of 0 is 0. So we can start our graph off at 0. Then I'm going to move over 1. What's the absolute value of 1? 1. What's the absolute value of 2? 2. 3, 3, 4, 4. You can keep going. Now, I only need 5 unique points. Now, you can't just use these 5 as your unique points because it's not enough information to draw the whole graph. Because when I go this way, negative 1, what's the absolute value of negative 1? It's also positive 1. And negative 2 is also positive 2. So if you just kept going forward and said, hey, there's my 5 points, this graph would look like a line, which is not what the absolute value family looks like. It makes this V shape, which we call the absolute value graph. Oh man, I went farther on the one side than the other. Oh, I'm going to have to live with that pain and embarrassment for the rest of my life. I would like you to write up here if this is an even or an odd function. So do we have reflective symmetry across the y, or do we have rotational symmetry around the origin? We have reflective. So this is an even. All right, square root family. So I want to think about square roots in terms of squares, but I want to think about them going the other direction. So let's start off, as always, with 0. What's the square root of 0? 0. So if you'll notice, every one of our graphs have a beginning point at the origin. All right, now just like before, I'm going to go over 1, which is essentially plugging 1 into this. What's the square root of 1? Is 1. Now, this is where this gets different than what we did in the other 3. In all these, we went over 1, then over 2, then negative 1, then negative 2. Here, I don't want to go over to 2 because that means plugging 2 into the square root, and the square root of 2 is 1.414, blah, blah, blah. It's not some nice number. Now, look, you can choose to move however you want. So I need to draw 3 unique points. So the other point that I'm going to go is I'm going to go to 1, then I'm going to go to 4. Why do I pick 4? What's special about 4? It's a perfect square. So I'm going to go over 1, up 1, over 2, no, over 3, no, over 4. What's the square root of 4? 2. And now I found another nice lattice point. And then from here I can make my sketch like this. Notice, why didn't we put in any of the negatives? Well, what's the square root of negative 1? No good. Square root of negative 2? No good. You could not square root a negative. So, I mean, if you think about it, this should be the inverse of this graph. So there should be another part down here is really where the negative piece should go. But because that would violate the vertical line test, mathematicians have just chopped off that portion. All right, is this odd even? Does it reflect over the y-axis? No, there's no branch over here. If I rotate this 180 degrees, it would point down here like this, which would be a different looking graph. It has to look exactly the same to be odd. So this is neither odd nor even. All right, the last two the reciprocal function and the reciprocal squared function. So the reciprocal function, the best way I can explain this is to think about it in terms of plugging in values and getting weird stuff out. So like for instance, let's plug in 0. What's 1 over 0? Well, wait, that you can't, right? 1 divided by 0, that's, remember our 2 ways to remember it? We've got 0, and then we've got 0 on the top and 0 on the bottom. 0 on the top is okay. 0 on the top is 0. 0 on the bottom is no good. What's our word for that? Undefined. So if I put a 0 on the bottom, I get 1 over 0. That's undefined. That means when x is 0, we don't have a function value. There are no function values when x is 0. We call this thing an asymptote. So I'm not sure if you've heard that phrase before, but this is called an asymptote. It's a line, it's a boundary line that our curve can never cross. Our curve gets closer and closer and closer to it. Now think about this. 1 over what number would ever give me an answer of 0? In other words, is there any number, 1 divided by any number, is there any number that you could think of to divide 1 by and get an answer of 0? Well, the temptation is to say 0, but we just said that we can't have 0 on the bottom. So 1 divided by 1, no, that doesn't work. That's 1. 1 divided by 11, that's 1/11. That's a number. 1 divided by negative root 2, that's some weird number. So there's no number that I could ever plug in for x to ever get an answer of 0. That means my y values will never equal 0 either. The reciprocal function has 2 asymptotes. It has a vertical asymptote at x equals 0, and it has a horizontal asymptote at y equals 0. That's why I say you must draw these asymptotes. Now, we got to talk about the curve itself. I'm not going to be super picky about what your graph looks like here. You just have to get it in the right quadrants. I'm going to think about it in terms of this side of x and this side of x. Because when I think about this side of x, when I plug in positive x's, what's 1 divided by any positive number? It's positive. So that means all of my outputs, when I input positive x, I'll get outputs that are also positive. That means all of my points have to live up in this section. Now, I can't violate the vertical line test, so I have to somehow draw all the points up here, and we've got to get infinitely close to this, and we've got to get infinitely close to that. So what we get are these 2 branches, they're called, of a hyperbola. So this is 1 branch of the reciprocal function. Okay, let's go to the other side now. These are negative x's. What's 1 divided by a negative? A positive divided by a negative is a negative. So on this side, we're going to get a graph that does the same thing, except it's going to be in the negative section. Okay, so using that as a guide, see if you can at least talk yourself through. Maybe you don't want to write it because this is something that we're going to use on our test. But at least talk yourself through. See if you can figure out what the reciprocal squared graph looks like. I'll give you a hint. It also has some asymptotes. All right, let's see how you did. So I've got, did I just do it? I'm just going to do a nice light blue. I just use green. I'm going to go with a red. So when I put in 0 on the bottom here, that's no good. So I'm going to get another vertical asymptote here through x equals 0. Now, am I ever going to get an answer of 0 out of this? No. So I've got another horizontal asymptote at y equals 0. Now, I'm going to use the same sort of conceptual thinking here. I'm going to take all these positive x's, and I'm going to plug them in. So what's a positive squared? Still positive. What's a positive 1 divided by a positive number is another positive. So this branch is up here. Like I said, you don't have to be super fancy about drawing it as long as it looks asymptotic at both ends and that it's up in this section. Now, over here is where things get interesting. These are negatives. But when I plug those negative x values into this x, I'm going to square them. So what's a negative squared? That becomes a positive. So what's a positive divided by a positive? That's still positive. Now sometimes you'll see that this thing is called a hyperbola, where it's got two branches, and the two branches will always be kitty corner in reciprocal world. Reciprocal squared, this doesn't have a name like hyperbola. We call it a superbola in my class, but I think reciprocal squared would probably make sense if you're taking another class outside of mine. Nobody else would know what a superbola is except us. Okay, so real quick, will you write? Is this an odd? Are there any odd or even functions, or neither? Odd, even, or neither? Pause it if you haven't yet, because I'm going to go. All right, first one. Does it have a reflective symmetry across the y? No, this doesn't mirror over there. Does it have rotational symmetry? If I took this whole piece of paper and rotated it 180 degrees, would it look the same? The answer is yes. So this is an odd function. Does this have reflective symmetry across the y? Yes. So this is an even function. All right, like I said, keep this somewhere handy. You will be able to use it on the test, but don't add anything unless you ask me first. All right, so now let's go back to our notes, and we're going to use our parent function sheet to help us guide how to graph these. All right, so first of all, I usually do the shift first. So I find out where the shift is, and I apply that to my transformation, my transformed function. So if there's anything added or subtracted, that's going to be a shift. So this is a shift to x, and remember it does the opposite of what it says. This is a shift in the y direction, and it does the same as what it says. So I'm going to shift -3 and then -4. This is my new 0, 0. I know it's not really 0, 0, but we're going to pretend like that is the 0, 0 of our parent function. You can also kind of think about these. Once you've shifted them, you can kind of just cross them out. They really don't matter as long as you work everything from this spot. All right, now that we've done the shift, what family is this? Well, it's a square root, so we go to our parent function sheet, the graph with the square root around it, that's called a square root family. So the name of this is square root. So how does a square root move? So I'm going to think about it two different ways. The first way is I'm going to look at this, and I'm going to see how this graph moves. So it goes over 1, up 1, over 4, up 2. But I've got a multiplier out front, which means I've got a stretch, which means all of these heights are going to get multiplied by 3. So this is at a height of 0, so 0 times 3 is still 0. But then 1, this is at a height of 1, times 3 will be 3. This is at a height of 2, would be at a height of 6. So I'm going to go back over here now. This is my pretend 0. When I go over 1, normally I would go up 1, because what's the square root of 1? 1, but we've got a multiplier of 3. Another way to think about this is to cross these out once you've done the shift, and then plug in the number here and see what you get. So when I plug in 1 square rooted is 1 times 3 is 3. So when I go over 1, I'm going to go up 1, 2, 3. There's my next point. Now, because this is a square root, look at my must graphs. In the square root family, you only need 3 points to determine if you've got the right graph. So we've got 2 of them. We've got to find the next one. So how far do I want to move over? I don't want to move over 2, because 2 is a crappy number to square root. So I'm going to pick 4. 1, 2, 3, 4. What's the square root of 4? 2. But I have a multiplier of 3. So that height of 2 is going to get multiplied by 3. So I'm going to go up 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. This is my transformed curve. If you feel like you could do it, pause, try to do this on your own. If you want to do another one together, let's talk. So let's look at our family first. So, or actually, I think I'm going to do shifts first. I think I like doing that. I think that's the most straightforward. So we've got a shift here of opposite, same. So back 2, I'm not going to circle and write anymore. So back 2, down 1. These brackets mean absolute value, so that's my family, absolute value. And once you've done the shift, you can kind of cross those out and then plug and chug. So when I go over 1, the absolute value of 1 is normally supposed to go up a height of 1. But we've got a multiplier of a half. That's going to take every height and make it half as tall. So when I go over 1, I'm only going to go up a half. When I go over 2, normally I go up 2, but I'm going to cut that in half and go over 1. Now, I know the absolute value parent function is supposed to make a v, so the other points I'm going to do on this side. So -1, absolute value is 1, half of that is 1/2. -2, absolute value is 2, half of that is 1. Now I grab my straight edge to make everything look fancy. And I've got a nicely transformed absolute value function. Now, only in the absolute value world, because these are 2 linear branches, you can think of this as slope if you want to. So you could have also gone up 1 over 2, up 1 over 2. You could have done it that way, but you got to remember that it's an even function, so that up 1 over 2 will become up 1 back 2 when you draw the other side. But I like to think about my functions as movements away from 0. All right, so if you didn't try this one on your own, I definitely want to encourage you to try this one on your own. So pause it, give it a whirl. Okay, let's see how you did. So my shift is on. This is going to shift forward 1 and up 5. 1, 2, 3, 4, 5. So my family is something squared. We call that the quadratic family. Okay, when I move over 1, what's 1 squared? It should be 1. So I should go up 1, but my multiplier is -2. So instead of I go that up 1 gets multiplied by -2, so I'm actually going to go down 2. Over 2 should go up 4, but that 4 gets multiplied by the -2, so I'm going to go down 8. 1, 2, 3, 4, 5, 6, 7, 8. Now this time I know quadratics are even functions, so I'm going to draw the rest of mine using symmetry. And don't forget to actually draw the curve. What do you think? I think this one's pretty straightforward. Why don't you try to do this one on your own too? So pause it. Let's see how you did. All right, the shift is on. Back 2 plus 1. This is the cubic family. I'm going to cross those out. Those are all done. So 1 cubed is 1 times a -1/2 would be -1/2. All right, 2 cubed is 8, -4. 1, 2, 3, -4. So I'm plugging in. Once I do the shift, I treat this as 0, 0, and then I just plug in 1, 2, then -1 and -2. So -1, that would be -1, then -1/2, that would be +1/2. Then I'm going to use oddness. This should rotate. So over 2 down 4 would be back 2 up 4. That cubic function is an odd function. So I should have rotational symmetry according to the origin. And I know it's not really the origin, but this is our pretend origin. So your graph should look like this. So now when we try to draw the reciprocal functions, remember that you need to, the rationals, reciprocals and rationals are the same kind. This says x and y intercepts. I actually don't care about that. If you want to cross that out, that's fine. I just care about the asymptotes. So as I look at this, where are my asymptotes? So the shift is on. This is next to x, so that's going to shift in the x direction. It says -2, which means +2. This is with y, so +2 +2. This is my new 0, 0. So when I look at my parent function, is this reciprocal or reciprocal squared? So I've got an x on the bottom, but that x on the bottom is not getting squared. So this is just the reciprocal family. And it doesn't really matter at this point because in both of these scenarios where there's an x on the bottom, we have a horizontal and a vertical asymptote through 0, 0. So my new 0, 0 is up here. That means my horizontal and vertical asymptotes are also going to be there. Okay, the reciprocal family, positives go on the positive side, negative goes with the negative. So positive x's go with positive y's, they go up. Negative x's go with negative y's in reciprocals. They're always kitty corner. But we have a multiplier of a negative here. So that's going to take these positive values that are supposed to be positive, and they're going to become negative. So this section is actually going to be down here. Now this is what I'm talking about. I probably am supposed to hit that point right there. I'm not going to get picky about it. As long as you draw it in the right section, I'm happy. Now because this is reciprocal and not reciprocal squared, the other one is going to be kitty corner, so it's going to be up there. They're always going to be on diagonal from each other. And if you don't want to just think about it as a process, you want to understand it, these are negatives, but a negative divided by a negative ends up being a positive. So let's see if you can do the next one on your own. What color haven't I used? How about a nice blue? All right, so the shift is on, forward 2, down 1, and then this is the reciprocal squared family. Reciprocal squared. And then there's no negatives, so there's no reflecting. So my branch is the positive side is going to be positive. The negative side, now look, some of these are actually positive x's. I know, but I'm treating this as a 0, 0. So this would be the negative side, and a negative squared would become positive as well. If I were to guess, these last two are the toughest ones. Those are the ones that most people get wrong. And then this one you have to be in class to get. Ask one of your classmates. You don't have to try to actually do that one. It's just a joke. All right. Good luck.